Cool. So as mentioned, my name is Christine Spang, and today I'm here to tell you about the email sync engine that powers Nihilus. It's built 100% in Python, and to date has synced and served over 10 billion emails for our customers. So let's get started. Oh man, hate it when it does that. An overview of what we're going to be talking about today. First, I'm going to give you a little bit of context about what exactly Nihilus does and why did we actually build an email sync engine in the first place. Then I'll be giving you a high-level overview of the technical architecture and specific motivations that made it end up the way it was. Then we'll be taking a bit of a deeper dive into some specific technical challenges that we've solved over the last 4 years. And I'll be wrapping up with a short discussion about problems that we haven't yet solved and things that we're planning to work on in the future. Nihilus was born out of the frustration of developing with email. Email is a treasure trove of data. From photos your sister sent you, to event tickets, personal communications, meeting invitations, and more. I wanted to include some screenshots of some serious business work documents in this, but our lawyers wouldn't let me. 6 years ago, I was working at a little company called Caseblaze, and I wanted to automate something that we were doing as a manual process. Namely, our sign-up system would send us emails when customers signed up, and then we would have to go and manually create leads in our internal CRM so that sales and customer support could know to reach out to these new customers. So I wanted to automate this, and what did I do? Well, I used this little C program called FetchMail, which downloads emails from an IMAP mail server. We were using Google email at the time, so it downloaded emails from Google. And then, and don't judge me on this, it was a long time ago. It delivered those emails to a Perl program that I wrote, and parse those emails using a MIME parsing library from CPAN, the Perl module repository. And then I extracted the data that I needed and posted it to the REST API for our internal CRM, and the process was done. I was automatically creating leads for every new customer that signed up. I'm sure a lot of you have hacked together similar little systems. And it works pretty well, as long as the problem that you're solving is highly constrained. In this case, I knew exactly what the emails that I was trying to parse would look like. And I only had to interface with one email system, Google IMAP. So that made it easy to put together a system to automate what I wanted to do in a pretty short amount of time. But what happens if we had to drop these constraints? Say, I wanted to take this system and generalize it so I could build a SaaS service that would allow anybody to connect their sign-up system to their CRM. Here's where things get a lot hairier. Say, I wanted to not only support Gmail, but also Office 365, ancient large companies which have like a dusty Exchange server in some corner of their data center, iCloud, open source IMAP servers like Dovecot or Cyrus. It gets really complicated when you try to support all of these different servers and you're trying to look at any email that might be in a mailbox. So say I'm gonna try to build this service. First, I have to allow someone to connect a mailbox to the service. There's no standard way to take an email address and turn that into the settings that you need to actually connect to the mailbox. So you have to use heuristicks or look up the host name in DNS or hard code settings for the major providers. Then, once you have some settings, you have to actually authenticate the mailbox. There's a couple different protocols that are in use. Some servers use OAuth. Some require you to just use a password authentication. And even once you've managed to authenticate, you're going to have to deal with crazy non-standard error messages that the IMAP server sends you. In fact, you'll probably end up having to parse text in order to figure out what the hell the error message meant, because there's no error codes that it sends you back. Once you've managed to authenticate the mailbox, then, because you want to support all of the different mail servers out there, you have to deal with many different protocols. The major open source open protocol is called IMAP-v4. It was released in 2003. And one thing you need to know about building with IMAP is that IMAP supports a lot of extensions on top of the base protocol. And servers may support some, all, or none of those extensions. Gmail also uses IMAP, but the way that Gmail treats labels doesn't map very well onto the IMAP spec. So you also have to special case Gmail for IMAP. Now, if you want to work with Microsoft servers, you have to use the protocols supported by Exchange. The first one that was also released in 2003 is this thing called ActiveSync. It was built for syncing mobile phones. And the wire protocol that it uses is this crazy thing called WBXML. That's actually XML encoded in a binary format and sent over HTTP. If the server's a little bit newer, you might be able to use something called Exchange Web Services, which, unfortunately, is also XML, except for you get to experience the joys of SOAP. If you're building for Exchange, you also have to deal with the poor library support for those protocols. There might not be a library to support the protocol, and if there is one in the language you're building with, it might not be very good. Fuck that shit. And once you've gotten the message off the wire, it's not over yet. Email has existed for over 50 years at this point, and functionality has essentially been layered on over the decades in more and more specifications as computing has changed. Plus, messages are encoded on email clients, and there are dozens of email clients out there. And you know, if you ever let anyone build another email client, they're going to send something that's broken, and then other email clients have to deal with all that broken encoding. Here's a list of a few of the different protocols, or not protocols, encodings and formattings that you'll have to deal with when parsing email. There's MIME, base64, 7-bit ASCII, because when email was started, there was only ASCII text, so 8-bit encodings were added later. Quoted printable, plain text, HTML. Headers might be folded over multiple lines or contain encoded words, which is a way of sending 8-bit text using only 7-bit ASCII. Plus, there's ways of encoding attachments. It's a mess. Here's an example of an actual text email, a raw email, with some of these things highlighted. And here's an example from our code base where we're trying to work around some issues with parsing headers and the complications that arise. You'll note that the number 3 in the comment says, "Everything is terrible." We use Flinker, a MIME library built by Mailgun, which sends a lot of emails. But we've still encountered emails in the 10 billion emails that we've synced that break Flinker. There's lots of crazy shit out there that your parser has to be able to parse. Plus, if you want to build some integration that actually sends email for a user, then you have to deal with an entirely different protocol that you haven't been using yet. It's called SMTP. For Exchange, you don't have to deal with a different protocol, but you do have to deal with the fact that Exchange servers will rewrite the message that you send it when it's sending. And sometimes this can mangle the message in weird ways. Here's another example from our code base where we're working around the fact that Exchange mangles new lines if you use certain encodings. To summarize, building for the generic case really sucks. If you have to parse and filter many non-specific emails, or you need compatibility with many different email providers, the amount of effort that you have to put in to build everything from scratch takes like 100 times more time. Holy crap, all I wanted to do was read some emails in a mailbox. It'd be really cool if I could just like make an HTTP request, or even get a webhook that notifies me when a mailbox has new email arriving. This is the problem that Nihilus was built to solve. Nihilus is a modern REST API that abstracts over 50 years of email history and makes it an order of magnitude easier for developers to build things that integrate with email. Let's talk a bit more about the technology. Here's some stats on the basic technology we're using. So we're still on Python 2.7. Major libraries we use include Flask, gEvent, SQL Alchemy, and PyTest. Other things we use in our production architecture, HTTroxy, Nginx. We run the Flask app under gUnicorn using the gEvent PyWizG adapter. Our primary data store is MySQL, which we mostly manage ourselves on EC2 with primary replica clusters. We manage access to MySQL using a SQL proxy called ProxySQL. We use Redis for caching and queuing. And we orchestrate our provisioning and fleet orchestration using a configuration management system called Ansible. Now, if you're looking at this list as a whole, you might notice the fact that none of this is like super weird. In fact, you might even call our major stack boring. If you've ever read Dan McFunley's incredible essay, Choose Boring Technology, you'll have seen this quote before. He says, let's say every company gets about 3 innovation tokens. You can spend these however you want, but the supply is fixed for a long while. We decided in the early days that we didn't want to spend our innovation tokens on things that were going to keep us up at night. So we chose technology that had survived the test of time and was battle-hardened already. This allowed us to spend more of this innovation actually working on the product and the problems that the product was solving. The one thing that stands out in this list as maybe a little bit weird or esoteric is this thing called ProxySQL. And I'll be talking about this a little bit more later, but the reason we chose to use something a bit cutting edge for accessing MySQL is because one of the first scaling challenges that we had to solve was the fact that we're dealing with a lot of data. Every email account might have tens of megabytes or gigabytes or even tens of gigabytes of data. So we had to deal with data storage as a problem very early on. Why do we have so much data? Back in the fall of 2013, when it was just me and my co-founder Michael hacking in his apartment, we considered a number of approaches for building the sync engine and API. There were basically 2 options. One, we could store minimal data and, for the most part, act as a translation layer between clients and email providers. Or the second option is we could mirror the contents of mailboxes and serve as many requests as we could directly. The first option would be way cheaper. People have tons of email, as I mentioned before. But the problem was that we really wanted to build something that would allow developers to use us instead of talking to email providers directly. And that meant we had to be really reliable and also relatively fast. The first option wouldn't allow us to accomplish those goals for a number of reasons. One, networks are inherently flaky, so we didn't want our reliability to essentially be the uptime of our service times the uptime of the network link times the uptime of the service that we were talking to. Plus, IMAP servers aren't super fast themselves, and we didn't want to have to actually start a new connection within a connection and wait for it to finish in order to actually just serve whatever data we were trying to serve. Plus, in order to simplify the complexity, we weren't sure that it was going to be the case that requests that we wanted to serve would easily translate into IMAP or Exchange server commands. So we decided that we had to go with option 2 even though it's going to be a lot more expensive. And we'd have to figure out a way to make the business economics work with this more powerful way of syncing email inboxes. It allowed us to achieve our goals of being reliable and fast. Here's an overview of our basic architecture. Again, one of the things that we had to solve early on was the scalability of our primary data store. So you'll see that we have a number of sharded database clusters here. We also have a global database that keeps track of things like developer accounts, apps that they've created, webhooks that they've created to subscribe to. And that database is a lot smaller, and we're able to have gotten this far by just scaling it vertically. I like to call the architecture of our actual application something that I call semi-monolithic, in that we have many different services, and those services live on different fleets of machines. But a lot of the code that they're running is shared between services. For example, everything uses the same shared database models to talk to the database. But they have separate launcher scripts, separate entry points, and we do capacity planning separately for different fleets. So, for example, we have a fleet of machines that serves our API that runs the Flask app. We also have a fleet of machines that when a new account is connected to our service, starts continuously syncing that account in the background and keeping our data store up to date so that we can then serve requests for that account. We also, again, use Redis for some caching and queuing. And it's a pretty standard setup for clients talking to our API. And all of our external points of presence go through HA proxy. All right, now that we've gotten through the overview, let's dive a little more deeply into some specific technical challenges that we've solved over the last 4 years. To start out, I wanted to talk a little bit about the philosophy that we kept in mind while building the API. The entire premise of the company is that clients should have to build one integration, not many. This meant that consistency and working around the edge cases and differences between IMAP and Exchange servers was very important. We had to do extra work to make sure that the API is unified as much as we could across providers. As an example, I mentioned earlier that IMAP servers have lots of different extensions. We didn't want people to have to think about IMAP or extensions. So we built different implementations of email sync that worked with these different extensions. And clients to us end up making the same requests to sync email no matter what extensions the IMAP server supports. Another thing that we had to work around and unify was the fact that many email servers don't support threaded conversations. So you're probably familiar with threads if you use Gmail or Outlook. But servers like iCloud don't give you a thread for an email message when you download it. So we had to implement our own version of threading in order to make sure that threads were universal for any email inbox that we were syncing. There were some cases that we found that we couldn't work around differences between email providers. And we had to document these differences and teach developers how to deal with them. One example from early on in the company's history is we thought it'd be really cool if people didn't have to think about folders versus labels. And we tried to unify them into an API that we called tags. Unfortunately, well, let me back up for a second. The difference conceptually between folders and labels is that on Gmail, you can apply an arbitrary number of labels to a conversation, whereas on other IMAP servers or Exchange, an email conversation or message is expected to be in only one folder at any given time. This is really subtle, and we thought that we could work around it, but we were wrong. It resulted in lots of bugs, confusing behavior, and luckily at the time we had only maybe like a dozen customers, so we were able to deprecate and get rid of the tags API and split it out into a separate API for folders and a separate API for labels. And then train our customers that they had to special case whatever they were trying to do, whatever they're using folders for, whatever they're using labels for, they had to come up with how to handle that on email servers that used folders or email servers that used labels. Hopefully, we learned a bunch from having to do that because there's a really painful migration, both in terms of moving all the data and also in terms of the work that we had to do with our customers to get them migrated over to the new system. Again, a brief overview of our database sharding. This is basically the first scaling problem that we ran into. It's basically like, so every email inbox might have a couple gigs of email, and say the disk size limit on running a MySQL database is like 5 gigabytes or 5 terabytes. There's only so many accounts that you can sync before you start running into these limitations. So we ended up sharding our database in the early days. And I'm not going to get into too many details because I've actually already written this story up. And I don't want to bore you with last year's news. But the TLDR is basically that we shard by account as the unit of sharding. And we use 64-bit primary keys and encode the shard ID in the upper bits of the primary key. This allows us to split things across shards and have the application know where our data lives without having to have a separate service that will map accounts to which shard they're on. It's pretty simple, and it's been really solid and works really well for us. The second part of our architecture that I wanted to dive into more deeply is this thing that we call the transaction log. One of the things that we wanted to do to make lives easier for developers when working with email was make it possible for clients to sync all or part of an email inbox locally without having to deal with the complexity of dealing with a document-based data store. In servers like IMAP, they were basically designed for a time when clients were expected to be online basically all the time. Whenever you're checking your email, you're going to be online. You don't need to deal with that data if you're not online. This turned out to be a bit of a pipe dream in terms of like network reliability and also the amount of data involved. So these days, most email clients implement a caching offline sync using IMAP, but this ends up being really kind of chatty and inefficient because an IMAP mailbox is essentially like a list of documents that are messages. And there are some newer extensions that make this a little bit easier by having basically like a modification sequence for the mailbox that allows you to query for messages that have changed since the last time you synced. But in general, it's like there's an entire RFC that tells you how to implement sync using IMAP v4. We wanted to make this a lot simpler. So what we do while we're syncing is every time we get a new change to a mailbox, we record that change in another table. This allows us to essentially like make that feed available to clients, and they can sync simply by taking all the changes that we've recorded and replaying them. We use this internally to power webhooks. So whenever new messages come in, that new message gets an entry recorded in the transaction table, and then the webhook service sees the transaction and sends the webhook to the client. Here's a diagram of that in action with webhooks. It's pretty simple. We actually use SQL Alchemy's ORM hooks to implement this. And we also truncate this transaction log after 30 days because keeping the history forever would be absurd in terms of the amount of data that we were storing over time and just egregiously expensive. Here's an example of some actual entries from that transaction table. For the webhook service, for example, we use the IDs of these transactions as a pointer. And we make that service reliable by only updating this pointer once we're sure that the webhook has been sent successfully. Now, if you're still with me through this, you might be asking, why on earth did you use MySQL for this? So the first answer to that is, one, we're a startup. The second answer is a little more nuanced. At the time, about like 3 years ago when we built this, we were really hyper-focused on keeping things really simple, because that would make our lives easier operationally. It would also allow us to iterate on the product faster, and we weren't even sure if this was like the right abstraction to be using. So using MySQL, when it was already our primary data store, was one fewer thing to set up, to learn, and to maintain. We already were hiring DBAs that knew how to operate MySQL, and we didn't have to hire some people that learned some other technology. It also was simpler because we could use MySQL's transactions to maintain atomicity, such that we weren't writing transactions for data that we didn't actually end up committing successfully. So if you put it in the same transaction, then if the sync process fails somehow in the middle, your transaction just won't complete and the transaction won't be written. It's a little bit confusing because I'm talking about MySQL transactions and our mail transactions at the same time. But the MySQL transaction would not complete, and therefore the erroneous transaction entry would not be written. And we were pretty confident that because we had awesome ops chops with MySQL, that MySQL wouldn't lose our data. And that's really important. But we know that MySQL is really not the right tool for this job. We really want some sort of distributed log that all these services can get push notifications when there's new data, and then they can send or do whatever work that they need to do. With MySQL, it's not very scalable because every single service that we build has to poll this table in order to figure out if there's new data. So one, you have to be careful about polling too frequently because that increases load on the database. And secondly, this makes there be more locking that's happening on the database, which also is not super scalable. We're pretty convinced that in 2017, the right tool to be using for this kind of thing is a distributed log called Kafka. You've probably heard about it. And we're just starting to do some early experimentation with moving some services, with replicating some of this data into Kafka and moving some services over to using it. The next thing I wanted to dive a little bit more into is what exactly happens on individual machines in our sync fleet. So we're syncing tens of thousands of email accounts, and we have dozens of machines that are syncing those email accounts. And we've distributed all of the load of those email accounts across all of these machines. Each machine is a multi-core machine, and one thing that you have to keep in mind when using Python is that because of the GIL, you need to use multiple processes if you actually want to make proper use of those multiple cores. So on every single machine we use a number of different processes, and our way of assigning mailboxes to an account sync basically goes host and then process number. So those two things tell our system where an account is going to be syncing. Within an individual process, we use a coroutine library called gEvent, which you've probably heard of. It's super solid. It's been around for a long time. A lot of really great production software has been written on it. So we use gEvent to sync multiple accounts on the same process. One thing that's a little bit tricky about syncing email accounts is that IMAP essentially requires that if you want to keep your mailbox up to date in real time, you kind of have to have a socket open all of the time. And if you're syncing tens of thousands of email accounts, that's tens of thousands of sockets, and a lot of overhead if you were going to have, say, a separate process for each account. We decided that was going to be too expensive, so we used gEvent to load about 100 accounts onto each individual process. This minimizes the overhead that we have to pay in terms of memory and also just in terms of using the operating system scheduler to schedule all of these. If we had a process per account, that would be a lot of processes. Here's a diagram of what an individual process looks like on one of these machines. So each of these green boxes is a G-event greenlet, which is basically like a microthread. And we have a top-level process that basically manages everything that's happening on that process. Then for each account, we have a child greenlet that manages the sync for that account. And it's the case that with these protocols that are used for syncing mailboxes, you need to sync basically individual folders separately. So that means on an Exchange account, we actually have a separate greenlet for every single folder on that account, because that's the way the email sync works. For Gmail, things are a little bit simpler because you can work around that by just syncing the all mail folder. But our API also supports syncing calendars and contacts. So those greenlets will also be managed by the parent greenlet that manages everything that's happening for that sync. These parent monitors are in charge of things like retrying stuff when it doesn't work. We do a ton of interfacing with networks. Basically, all of this is like network I/O. And there's constantly things that are failing, whether it's due to like DNS errors or like provider being down or just like the link is flaky. So we wrap a lot of our code in functions that look like this. It's basically a higher level function that wraps a function, and you tell it like classes, like exceptions that you should try again, and exceptions that should be fatal. And then, as we all know, that most of programmers' time is spent doing error handling and adding backoff. So this function has a built-in exponential backoff, and you can configure configure some parameters about that backoff. We have a couple dozen machines that are syncing all of these different accounts. And one challenge that we've run into is figuring out how to distribute the load of syncing all these accounts across all of those machines. One thing about email is that each individual email account is different from almost all the rest. We have different syncing implementations for different protocols. And email inboxes also vary a lot in terms of their size. They might have, say, 1,000 messages. Some of them might have 1,000,000 messages. Some of them might be receiving new email like 15 times an hour. Some of them might only receive email like once a day. Sometimes they receive email even more than that. And we found it really difficult to predict how heavy an account will be just based on like aspects of the email inbox itself. So what we've ended up doing is basically measuring the amount of time that a single account has active greenlets that are syncing it, and using those weightings that we've actually measured in order to distribute load over the fleet. And at this point, it's a pretty heavy process actually to move accounts around, because like when you start up an email sync, you have to like calculate a bunch of stuff and like ask the server for a bunch of information, and just like booting up the email sync is pretty expensive. So we don't do load balances very often. It's a manual process that we do right now, kind of like at our discretion when we feel like it's necessary. Because this is a heavy process, we aren't able to do super great automatic load balancing yet. And one thing that's interesting is that our traffic is very much tied to US weekday business hours, which is super great if you're on our ops team, because it means that most problems are likely to happen during the workday. But it does sometimes mean that we have like Monday morning load issues at like 7 a.m. because that's when the East Coast is like furiously answering all of their emails. One thing we'd like to do in the future is figure out a way for us to kind of smooth out this graph and make it so that we're utilizing our fleet more evenly. Maybe that will happen naturally as we kind of go a little more global. We'll see. So earlier I illustrated how we use Greenlets to sync individual accounts. And one challenge that has resulted from this is the fact that we have actually a lot of Greenlets that are operating in an individual process. So if we have like at least 3 Greenlets per account and 100 accounts per process, that's like a lot of stuff that's going on at the same time. There are Greenlets everywhere, and it's really hard to tell what they're doing. And that's bad because it means that we can't optimize our code because there's like a lot of things happening at the same time and it's difficult to tell what's going on. We've ended up addressing this problem by building a lot of our own custom instrumentation for working with Greenlets. One thing that you need to keep in mind when working with gEvent and Greenlets is that the event hub scheduling is cooperative. And unfortunately, sometimes code is not cooperative. So you have to keep an eye out for non-cooperative behavior and shut it down, or at least like make sure someone knows about it. We have some code that we use that does a couple different things. One thing that we do is we have basically like a monitoring Greenlet that runs in every process and will tell us when the event hub is getting too saturated. So there's this thing we call the congestion Greenlet. And this is actually the entire implementation of this Greenlet. And what it does is on every single process, we have this one congestion monitoring Greenlet, and it schedules itself to run every so often. And it keeps track of the time. And every time we get around to running this Greenlet, if it's been too much time since the last time it got to run, it will send an event or like send a log to our monitoring systems, which basically means like either something is blocking or the event loop is getting too congested. There's like too much stuff happening at the same time, and like the event loop can't go all the way around and get through everything that's scheduled in a reasonable amount of time. Delays are bad because a lot of our customers expect our API to be like semi-real time. Like they don't want to get notifications about emails like minutes after they were sent. They want it to be seconds. So we need to be pretty vigilant about making sure that we're not like trying to do too many things, or there's like blocking code that is getting in the way of us having a highly performant system. This is just one example of some of the things that we've worked on. We also wrote some custom stack sampling code that effectively on each sync process, we also run a separate thread. And the reason it's a separate thread is because we don't want like broken shit that's going on in the email syncing Greenlets to be able to prevent the monitoring from working. So we use a thread for that. And we effectively collect stack samples at an interval on these processes in production all the time. And we serve those up over an HTTP server that's running on this separate thread. Then we have an internal admin tool that can go and fetch these stack samples from a specific process on a specific instance and generate a flame graph which tells us what the hell that process is doing. So this graph here essentially shows us the CPU usage breakdown of like when Greenlets are active, what their stack looks like. So it's basically like the CPU breakdown, but aware of gEvent and aware of Greenlets. So if you try to use just basic, like a basic profiler with gEvent, I wouldn't tell you the right thing because the Greenlets would confuse it. So we had to write our own instrumentation to analyze what was going on. We also have a mode of this stuff where it's aware of basically greenlets that are waiting on I/O, and it will show you the time breakdowns of inactive greenlets as well. Because if you only look at greenlets when they're active, that won't show you when they're like kind of like sleeping and waiting for a really long time for something. All right. So that was kind of an overview of a few different things that we've worked on and solved over the last 4 years. And there's a lot of things that I'm excited about that we're working on now and thinking about working on in the future. So I wanted to go through those real quick. The first thing that I want to talk about is MyPy. There's been a bunch of activity about MyPy at this conference. And one thing that we found as our code base has grown and engineers have come and gone is that maintainability can become an issue with Python over time. Our code base isn't even that huge, but it makes a big difference if you can look at a function and you can see what the data types are of the function parameters for that function without having to go and then dive through like 6 files to figure out where those variables originated. Plus, we're starting to kind of refactor a lot more and change existing code. And it's really useful to have confidence that when you're making a refactor and you're changing an interface, you haven't forgotten any instance of that interface. So an engineer from our team, his name is Mark, added support for MyPy to our linting setup. And at this point, we're at about like 10% coverage of MyPy. And it's pretty great that MyPy supports incremental coverage because it's allowed us to like start writing new code with enforced you must write type annotations for these new functions. And whenever we touch old code, we go back and we add type checking functions. If we had to do this all at once, we probably never would have started doing it because it's just like a huge distraction and rabbit hole, and like you can't really justify spending like a week adding types to your entire code base. But I'm really excited about the idea that in the future we'll have really, really solid MyPy coverage, and that's going to help us keep using Python as our code gets more complex. Another thing is, I mentioned in the beginning that we're still using Python 2.7. And the reason for that is that when we started the company about 4 years ago at this point, Python 3 wasn't as solid as it was today. There were still lots of major libraries that didn't yet support Python 3. And particularly, we knew we wanted to use gevent, and gevent didn't support Python 3 at the time. So we had to build the code base using Python 2.7, and that means that, well, we're really convinced at this point, with the momentum that Python 3 has been gaining, that we should start migrating and start using Python 3. We're working on a plan to do that gradually. What we want to do is effectively start building new services using Python 3 by making the core shared code of our code base support Python 2 and 3. And then effectively over time, our usage of Python 2 will go down, usage of Python 3 will go up, and we'll get to take advantage of a lot of the great performance and new features that are now present in Python 3. I also mentioned earlier that we're thinking about basically replicating this transaction log that we're currently keeping in MySQL into Kafka. And I think this will allow us to do a lot more cool and interesting things, and that's one of the reasons I'm super excited about this project. I think this will allow us to effectively like pave the way to an architecture that's more like microservices in the future. We avoided this in the beginning because honestly it was like super overkill, but as the team grows, having more flexibility over every service not having to talk directly to the database will be really powerful. And it will also prevent us from like adding weird extra processing directly into our like core sync loop, which means they'll be able to do things that require extra processing power, or like do extra analysis to data that we're syncing in without blocking the core sync. We also want to make our load balancing better. We're working on some product enhancements to both make the interface for webhooks a lot better and also add some new features to context and calendar. I also haven't talked at all about kind of like general observability, information security, and there's lots of other things that I think are really cool that we're working on. All right. So that's all of the material that I brought to share with you folks today. I wanted to, at the end, take a little bit of time to thank everyone whose work made this presentation possible. First and foremost, the engineers at Nihilus, both past and present. A lot of their work I've presented to you today. I also wanted to thank the authors of third-party libraries that we heavily depend on, specifically the Mailgun team who wrote Flanker, the MIME library we use, Menno Smits, who wrote IMAP Client, which is the IMAP library we're using, and last but not least, obviously, the Python core contributors. Thanks again for coming to my talk, and if you want to learn any more about this, you can feel free to check out our website. A lot of the code base is also open source, and you can dig through it on GitHub. And if you're interested in working on stuff like this, definitely come and find me because I'd love to talk to you.